Hi everyone. This is an updated laboratory video for the ETE335 associated with testing filters, and in particular we're going to look at a crossover filter, which is a very common filter in the audio world. Before we look at the update for the equipment, I'd like to talk a little bit about testing. As you know, testing is a critical part of all engineering endeavors, and often your first engineering position will involve some sort of testing function. So understanding good test engineering principles is important. In the modern field of systems engineering, testing is typically part of what is called a verification and validation, or V&V process. So what is verification and validation, V&V, in test engineering? Well, if you look up Wikipedia, you'll find an article associated with the Project Management Institute, and which has been adopted by ANSI, the National Standards Organization, and IEEE. And these are some of the definitions they give. So for verification, this is pretty straightforward. Verification is the validation of whether or not a product, service, or system complies with a regulation, requirement, specification, or imposed condition. It is often an internal process. So the key words in there have to do with specifications when we talk about engineering testing, and it's pretty much what you would expect. Does the device do technically what you expect it to do, or what is specified? We're all used to seeing specifications on devices, and so you're going to test for that. So an ETE graduate at Boeing once told me what verification means to him is, does the device do what you say it does in technical terms? So this is pretty straightforward. Validation is a little bit more fuzzy concept, okay? But from Wikipedia we have, validation is the assurance that a product, service, or system meets. It often involves acceptance and suitability with external customers. So it's similar to verification, but this is how our alumni put it. Validation means, does the device do what you want it to do from a user's point of view? So verification is the internal test. Technically, does the device do what you say it wants to do? And validation is, does the device do what you want it to do in terms of the user? Two similar and related concepts. So, on to the update for the laboratory. So this update is primarily because we just received in 2015 new equipment in the communications lab. We have a new arbitrary waveform generator from Regal and a new oscilloscope from Regal. We also got a new spectrum analyzer, which we'll talk about in a future lab. So signal generators are pretty straightforward, as you would expect. We have all the typical functions available: sine, square, ramp, pulse, a little more exotic in terms of arbitrary waveform generation. But we will use the sine wave. So select sine. If it's on something else, you just press sine and you'll see the details. The default condition here is 1 kilohertz. You get used to the reading of the screen there, 1.000, comma, a little more European style. The amplitude is 5 volts peak to peak, and there's 0 offset, and the phase is 0. Alright, that's fairly similar. So when we do a test, particularly with a filter, we like to use the highest input signal possible, because when you test a filter, the more difficult measurements happen to be at where the signal becomes very small, And so if you start out with a large signal, you can usually make better measurements. I'm going to maximize that value, which in this case is 20 volts peak to peak. So that will be the output signal. Now, our network is as in the other video. The input side is the red wires, the output side are the green and yellow wires. Review that video. So one of the important features on the modern digital instruments is that you must turn on the output function for this ARP. So don't forget to do this. Press output. Now the signal will be generated. If I come over to the scope, as most modern scopes, there's an auto function. So we'll press the auto button and we'll see the display. So the top signal is the yellow one, or the input. The bottom one is the blue, or the output of the crossover filter. So we need to identify a few measurements. So down in the bottom area, you can put some measurements. We need four values in our data. We need the frequency, which is already selected. You can see 1 kilohertz. We also need the input voltage, the output voltage, and the phase between the two. So let's go to the measurements. The measurements are following the menu on the left-hand side. You can see that I have the horizontal functions, I have which are the time functions, and the vertical functions, which are the voltage functions. So we want to select a voltage measurement, and we want to select the RMS value. So when we press the menu and RMS, we get an update voltage, and that says 1.18 volts RMS. Okay, you can translate that into peak to peak. For AC signals, I prefer RMS measurements because there's a little averaging that goes on in the RMS measurement, which tends to be more stable as a value versus peak to peak or other values. So we see 1.18 volts RMS for the first channel, which is the input. Now I'm going to select volts RMS for channel 2, or the output. But in order to do that, when you press measure, you need to select the source to be channel 2 for this measurement. So now I can go back to this menu and select volts RMS, and you can see, even in the color coding, that volts RMS on channel 2, the blue color, is 956 millivolts, or just under 1 volt. The last value we need is the phase. So phase is measured with respect to a reference, so we'll change the source to be channel 1. And then we'll go back to the menu. Phase is of time, or horizontal measurement. So we go to horizontal, and then the next menu down, we'll see phase. There's 2 of them, phase 1 to 2 rising, phase 1 to 2 falling. We'll select phase 1 to 2 rising, and we now have the selection of the phase. So we see channel 1 is the reference, and it's around 51 degrees. Now the display is a little fuzzy. You can clean it up by, under the acquisition or acquire function, you can select the sampling or acquisition to use averaging. When you select averaging, it'll tell you how many average. 512 is too large, but something maybe in the area of 8 is usually a good value. So we see a pretty clean measurement. Now averaging is nice because it gives us pretty clean looking signals. The problem with averaging is that it does cause a time delay. Here's an example. If I change the frequency on the device or on the input signal, you'll see that it takes a little bit in between the changing of the frequency. If I turn off the averaging and just make it regular, normal, see it goes back a little fuzzy. If I change, I get a much more direct change in the signal. But averaging is normally useful for you, so we'll select minimal averaging. Okay? Down at the bottom you see lots of data associated with your measurements. But the key is we have the frequency value, we have the RMS of the input, the RMS of the output, and the phase between them. So you can record those 4 values directly to your spreadsheet. The first value, the rise time, doesn't matter to us, but that's just associated with the trigger function. So you collect data and record it. Now, where do we start data-wise? Well, on a filter, it's always useful to start at a known frequency. So let's set up for measuring the high-pass filter and the critical frequency. Okay, so I'm measuring on the yellow wires, which is the high-pass filter. Don't forget the resistor, which serves as the load. Filters always need loads. And this is the display. If I zoom in on the phase, we know at the critical frequency we should have about 45 degrees. In this case, we're reading in the low 40s. Minus 42 is the average phase measurement. You can see that there is some variation in it. The average value will be a little bit, take care of a little bit of the noise in the measurement. So again, I use that. If you want to update that display, simply press clear, and you will get updated values. And those values should be fairly close to one another. Now, the critical frequency by calculation is 5.1 kilohertz. But we see that phase-wise, we're not quite at 45 degrees. If I change the phase a little bit, so 5.1 kilohertz was the calculated critical frequency, but we see that it's actually a little closer to 4.6 kilohertz. That's partially because of the resistance, partially because of the variation in the components. The RMS output is 1.1 volt, the input is 1.67 volts. The ratio is about 0.7, which is a good value. So it's always important to check that first known point. Now we can easily go back and change the frequency to values we want. So we will change this now back to 1 kilohertz and adjust for the condition at 1 kilohertz. So now we're back to 1 kilohertz. Now, there's a tendency with these automatic instruments to just press the auto button all the time. You want to avoid doing that because it resets all of your other functions like your acquisition. So use the time-based controls. In this case, we'll adjust the horizontal control. Now you see the signals have changed in height, right? So you want to maximize those as best you can. So I'll adjust the blue signal. I like to have on a filter, I like to see both signals compared to one another. So I'm going to adjust this time base so the two signals are overlapping with each other. The blue signal, which is the output, appears larger, but that's because it's at a 200 millivolt range and the input is at 1.48 volts. So I'm going to increase my input signal till I get a larger display. You can see some averaging going on. Pick something from convenient. Well, maybe something around 500 millivolts per division, and we have 200 millivolts on the output. If I make the two the same, you can see that the output is definitely less. Now, it's important in making measurements on scope you have the largest signals on the screen, which these are now almost the same on the screen. You'll get the more accurate values. So now we're set up, we're ready to take data. Record the frequency, the input voltage RMS, the output voltage RMS, and the phase shift between them. And then you're ready to graph your data.